All right. Welcome everybody to a Unity tutorial I put together. Well, there's not much of anything right now. This tutorial is going to be a beginner's tutorial with a little bonus activity at the end. And it's going to cover some basic stuff like getting your camera to track your player, as well as some basic movement. Okay, so let's first get started by adding a sphere as well as well, before I do that, Unity likes to just put it wherever it wants when you create it. So you can head over to the inspector and set it to 0, 0, 0. We're also going to add a cube. And again, zeroed out. So this cube is actually going to be our kind of platform for today. So we're going to make it kind of flat. So first we're going to scale it. 2 in the X, 2 in the Z, 1 in the Y. Actually, yeah, 0.5 in the Y, just to make it a little flatter. In fact, we can even go more than that, 0.25. And maybe elongate the sides a little bit. So as you can see, based on the X, Y, and Z scale, you can see that the X component of the cube got a lot flatter, whereas the X and Z got longer. And then we could just put our ball a little up here, about 0.6. And it'll fix itself. We're using the physics engine once the game starts, so there's no need to worry about it too much. Okay, so I've put this basic movement script in the description, but I'm still going to go over it. I'm not going to write it because, actually, you know what? Might as well. Okay. So this is what it looks like before, so you can pause here if you want, or if you want to see me type it again, I'll do that right now. Okay. And there we go. Okay, so the first thing we want when starting a game is to have a camera that follows us. And you might think, oh, we'll just make the camera a child of the sphere. That kind of works, except the problem is when the sphere rotates, the camera's going to rotate, and it's going to make the viewer puke. And I believe in the rigid body settings, you can constrain the rotation, but then that just gets a little messy, and there's a more elegant way to do it in code, so we're going to do that. The first thing we have to do is actually set up our camera to be in the view we want it to be. So you can see here is the camera preview, and it's much too far from our ball. So we're going to go ahead and drag it closer, get it up a little bit, and I'm using this with the W keys. Then I'm going to hit E and rotate it downward. So we're getting a nice kind of third-person view of our ball. And then once we're satisfied with where it is, we can go ahead and leave it there. And we're actually going to memorize that offset. So let's start coding. So we're going to have a vector3 offset here. And then we're also going to want a reference to our camera. So we're going to do public game object game camera. Don't name it camera because that's kind of like some reserved keyword that Unity uses, or the Unity engine. So public game object camera. All right. So what we want to do is when the game starts, we really want to remember. We want the program to remember this specific distance that the camera is offset from the ball. And even if we move the ball, we still want the game to keep that distance. So the camera is constantly kept away by this offset. It's kind of like the ball has a little invisible arm keeping the camera here and not pushing it further away or closer. So this is how we memorize that offset. When the game starts, we want the program to look at the position of the ball and set offset to the position of the camera. So we access that by just doing that transform that position. Oops, this should be game camera. That transform that position minus this dot transform that position. This being the object that the script is attached to, which will be the ball. So then we've now established the offset. So now we can use that offset in update. So the way we use this is that every frame we reset the position of the camera. We reset the position of the camera so that even if the ball moves, the camera is still looking over its shoulder. So in order to do that, we get the main game camera's position. So game camera transform position is equal to this transform position plus offset. So every frame we kind of remind the game camera where it should be by adding its the offset to the ball's position. So let's see if we can give that a try. So save this, head over to the script, and drag the script onto the sphere. Now you should see this this field. This is important. We haven't yet drawn a link. Game camera is just a name, but unless you actually tell Unity which camera game camera is, it's not going to be able to figure that out. And you can see that if we press play, we're going to get a bunch of errors. And unassigned reference exception. The variable game camera of movement has not been assigned. So to do this easily, we can just hit the circle. It's going to bring up a list of all the game objects in your scene. We can just double click main camera. Now we can see that game camera has been set to main camera. So if you press play, okay, so this is kind of expected. Let's try moving this ball. And there you go. No matter where I move the ball, that camera is constantly updating its position with the initial offset. However, if I rotate the ball, which is what's going to be happening during gameplay, the camera is only tracking the positional offset, not the rotational offset, which was what would be happening if we actually made the camera a child of the ball. Okay, now, to actually get the ball moving, we need to do a couple of things. First, we're going to make a new rigid body. A rigid body is the component Unity uses to apply physics forces to objects. And we can just call it RB. It doesn't really matter what the name is, just like it doesn't really matter that we called game camera. It's just something for personal reference, so we know what we're talking about. So first, we need to make a link between the RB encode and the rigid body component that the sphere will actually contain, and we actually will add that later in the inspector. So it needs to be, you essentially need to create a rigid body twice. So RB is equal to this dot get component rigid body, and yeah, that should be it. And now let's add the rigid body actually on the ball. So add component rigid body. And okay, that seems all good. And now we can actually start adding inputs. We can start reading inputs from the player and start applying forces to the rigid body. Okay, perfect. Let's do it. So the way you do this is you can essentially have 4 if statements. Each if statement will read W, A, S, or D, or the arrow keys if you prefer. So if input dot get key. The get key down is used for single detection. Get key continuously checks. Open parentheses key code dot W. open curly bracket, RB, remember RB is the rigid body, which lets us apply physical forces, dot add force. And forces are expressed in vector 3s. This is because Unity is three-dimensional, and that means that each 3D vector can have an X component, Y component, and Z component. Right now we're just going to use the X and Z component because we don't really want our ball to fly or tunnel down into the ground just yet. So that's the ones we're going to be focusing on. So if we wanted to move our ball straight up, we'd have to add a Z component to it. That way it let it move in the Z component, which is this direction, which I call up. It doesn't really matter what you call up. However, seeing as the camera is looking at it from this angle, if I press W and it goes left, for example, that'll be confusing. However, if I press W and it goes up, which is the direction away from the camera, and I can see here that that's a Z component, that's going to feel natural to me. So that, for that reason, I'm going to make W add a 3D vector with a Z component. So 0f for the X, 0f for the Y, and 5f for the Z. I'm using 5f just because I think that's going to be fast enough so that it's not very boring and not too fast so that it just rockets off into space. That's just from personal experience. Okay, so there I just copied it, no need to rewrite code. So W, A, S, D. Alright, now for A, so A is the left key on the WASD scheme, so that means I want it to move this way. And looking from the camera, that's going to be our negative X. Sorry, it's going to be a 3D vector with a negative X component, because again, that's the left direction here. S, I could analyze this, but S is the opposite of W directionally, so I just invert it, make it negative. Same thing for D. D is just going to be 5F, the opposite of A. Alright, save that. And yeah, it's that easy. Well, I'm not sure if you found it easy or not. Probably more difficult if you've never done something like this before. Anyway, just try it out. Okay. Oh, something seems weird to me. Okay, something's definitely weird. Let's see, I think I've messed up somewhere. So W is up in the Z. Oh, there we are. I seem to have forgotten to erase one of the components when I copied it. Okay, so let's review that. So D, right side, that means positive X component. S, bottom side, negative Z component. A, left side, negative X component. And W, top side, positive Z component. Let's try that again. And it's working. Perfect. Alright, so that covers the basic movement. The next half of the video is just more for fun, but if you watch, I think you're going to enjoy it and find it rewarding. Okay, so the first thing we're going to do is we're going to take this little island here. And we're going to make it just a bit smaller, and you'll see why later. And yeah, that seems good. And then using Control-C, Control-V, we're going to create a 7x7 array of tiles. I'm holding Control here, which snaps it in increments of 1 meter. So you can see that if I do Control-C, Control-V, and hold Control, because it's 2x2 meters, it takes 2 snaps in order to put it at the next kind of increment here. So let's keep doing that. So far, this is 4 long. That's 5. Six, 7, perfect. Now we can start duplicate. Now we can duplicate these all at once and move them. So 3, 4, 5, 6, 7. Okay. and there's 49, 48, but it doesn't count the first cube. Okay, now we're going to need some new materials. So I'll go over how to create those. Oh man. Oh, this is going to be painful. Okay, so to create any material, we simply go on create material, and I'm going to call this floor. So I like raising the metallic and smoothness all the way up. It kind of looks cool. And so right now it's black, even though the color is white. I had this I think this is a glitch with the version of Unity I'm using. If you get this error, go to rendering lighting settings and hit generate lighting. And that should fix it. So in order to actually apply materials, we need to click and drag them to the individual cubes. However, there's a better way to do it, which is probably what I'm going to do. So it involves deleting everything I just made and starting over. Unity has a prefab system which allows you to apply changes. It makes a prototype of a game object and then lets you modify that prototype, which is linked to multiple clones. So when you kind of modify the prototype, all the clones are modified as well, and that's known as a prefab. So to make a prefab, we simply click and drag this cube over to assets, and now this is a prefab. You can see it says prefab asset, open prefab. So we can head into the prefab editor. The lighting broke again. And then I'm going to take this floor material, I'm going to re-add it here. Then when I go back, you can see that it says no overrides because the material matches the material I set it to in the prefab menu. Okay, this is not strictly necessary. You could just click and drag the material to all 49 cubes, but that could get a little annoying. Also, you could have just added the material to the original object and then duplicated it. Right, let's go through that again. Maybe we'll just 25 this time. Or maybe not. Okay, now here's the cool thing about prefabs. If I change a property here, it changes the whole, changes all of the prefabs at the same time. So that's pretty cool. Let's also give the ball material. So again, create new material, applied ball, and put the metallic and smoothness knob, and then you can actually add an albedo map to it, which is kind of like a picture just paste onto it. So I have this picture of a hedgehog, and I'm just gonna put it on the albedo map. Finally, I take this ball and I click and drag it on the sphere. No need to make a prefab here, as there's only one sphere, so it would be kind of a waste. Let's just test it real quick, make sure everything is kind of working. Okay, beautiful. Now let's actually get into the meat and bones of this next section. So what I want to do is I want to make the ball change the color of the floor depending on the velocity that it's traveling at. And I'm going to go over how to do this. We're going to use a built-in method called void on collision stay. This will be called every frame that the ball is in collision with something. Yeah, it'll be called every frame that the ball is in collision with something. So we can actually access the object that the ball is colliding with by calling this little collision parameter variable and then doing .gameObject. So I know that the ball, the object the ball will be colliding with is the floor. So I'm going to do GameObjectFloor equals collision.GameObject. Okay. Now I want to change the color of the floor. So I'm going to do color old color, which is the old color that's going to be changed. We need the old color so that the color will iteratively change. If we don't have access to old color, it'll just bounce randomly, and that won't look very nice. Floor.transform.getComponent. The color is in the material, which is in the mesh renderer. Yeah, little hidden there, but it's necessary for how complex materials actually are. .material.color. Now we have a reference to the color. The reason why I pull the color and I don't just get the material is because the color is passed by value, the material is passed by reference, and I won't go into that more, but if you end up copying the material and you try to change it, it's messy. It's a bit messy, and it kind of goes into how C# is object oriented, but just know that if you just want the value itself, then you want to use primitives, which are colors and 3D vectors and stuff like that. Otherwise, you'll run into issues which other people could explain much better than I can. So then we're going to create a normalized color using this old color as well as the velocity. So we're going to make this a new vector 3, and I'm going to need 4 lines for this one. Yeah, get ready. So what we're going to do is we're going to take the old color's red value, and we're going to add the velocity of the ball to it. So we access the velocity by, again, calling this rigid body, and it just gives us access to velocity as well as its x, y, and z components. We're only going to be using the x and z components since that's the only components our ball is going to have. So we're going to add the x component to the r value. And not just x component, but first we're going to normalize the velocity. This way we're only getting the direction of the velocity. So if it's like something really high, it won't completely throw our colors out of whack. Normalizing it will return a vector with a magnitude of 1, and that's going to give you just the direction of the ball, which is really what we want. And then we're going to get the x component of that normalized 2D vector, essentially, because, again, there's no y component. We're also going to divide it by 20. Uni is kind of weird in that in code, the RGB values range from 0 to 1, not 0 to 255 like you would expect. It's still using that same system, except 1 would be like the 255 value, and 0 would be the 0 value. 0.5 would be like something in between, like 128, 127. So that's why I kind of have to divide this normalized vector by 20, because even if it only does have a magnitude of 1, if you add 1 to the red value, it's going to instantly make it red, and it's not going to look like it's subtly changing. So that's why we normalize this velocity component. Comma, let's move on to the next value. And this is the green value. And this time we're going to add the z to it. So, same thing as before. So this time the green value will be decided by your up and down motion, whereas the red value will be affected by your left and right motion. Now, with both of those out of the way, you're probably wondering, what am I going to do about the blue value? You'll see. So what I've decided to do here is I've decided to divide the x by 2 and add it to the z value divided by 2. Well, divided by 2 from 20, which is 40. So this way, the blue value is decided by your diagonal movement. These are, you feel free to exchange these, like this one could be the red value, this one could be the green value. Depending on what you make it, you're going to get different kind of color patterns, themes, whatever you're going to call it. Finally, at the end of this, we normalize that entire vector. This has the effect of making sure that your final color has no individual components greater than 1. Because again, that won't even register on Unity's color scheme, and it's going to actually save it. It won't give you an error, but it'll just have it so some colors will have red, green, or blue values greater than 1, which on top of having no effect can lock it into that color for a while, so it's not going to be as dynamic as it otherwise could be. Okay, now that we have this normalized color, we're going to make a new color. Because remember, this normalized color is actually a vector 3. We can only assign type colors to the color. Yeah, go figure. So new color. Here we're going to use mathf.absolute value. This is so we don't have negative values for colors. It does have the effect of making it irrelevant whether you're moving left to right or up and down, but oh well. And then we just take the x, y, and z value of the color normalized, and we set it here. Okay, and after we've done that, all we need to do is actually set it to the object. So again, we reference the floor, we reference the mesh render, we reference the material, color, and we finally save new color to that color. I know that was a lot, but I think you're gonna like it when you see what happens next. Oh, we forgot a semicolon. There we go. You get some really interesting designs if you decide to paint it in a circular motion. You're going to notice the same motifs popping up over and over again. And you'll see what I mean once I'm done getting it. So when I'm going from down to up, in other words, moving in a positive z direction, I get this light green color. When I'm moving down or right, it becomes red or violet. So when you paint the canvas in a circular motion, you'll notice that each of the corners have their own distinct region of color. And I found that really cool. So this is what I've painted. If I go in a counterclockwise manner, it might be useful to pull out your camera for this so you can see more of the canvas as you paint. Now you see that if I go in a counterclockwise manner, it's actually flipped. Which I find very cool. And there's a ton to experiment on this. You can try making the tiles bigger, smaller, just add more of them. Really, it's up to you. And that's what I really like about programming. Whoops, there it goes. That's what I really like about programming, is that even with just a simple, wow, that's really cool. It's like got a couple of triangles. Even with just 8 lines of code, granted they are a little complex, you can get something which almost looks like a work of art. Alright, I know that was a long video. If you watched the end, thank you. And it's my fans that always keep me going, and I just can't stress enough about how I appreciate you guys. It's it's just amazing the outpour of support I receive from you guys. All right, that's getting a little much. Sorry. I don't like the color of this one. It's yeah, there we go. Gonna cheat a little bit there. Oh, perfect. Okay, bye.